Hi, I'm Brian at teacher.com, and this introductory video is about circuits and Ohm's law. This topic is one where I'm going to try and make the video not too long, but I do have to go at a fairly slower pace, and I have to be very careful to make sure that I use the correct terms as we go through this. It's a very difficult introductory topic to do in a video that doesn't go on for an hour and a half. So let's get into this and see how it goes. We're going to start off by defining a circuit. And a basic circuit has to have three components. There has to be a source, a path, and a load. And in the illustration on your screen now, the battery is the source. It's where the circuit starts, is at the battery. And then the wires and the fuse, they provide the path. And the load is presented here as a light bulb. The circuit starting from the battery, flowing through the wires, through the light bulb, and then back to the battery, provide or create a whole circuit, a complete circuit. And if the battery is charged and the light bulb is good and the fuse is intact, we would then have a light bulb that would come on. That would be a complete basic circuit. Now the path between that source and that load can have a number of other components along the way, both going to the source and coming back. Again, starting at that source and going through the load and back, okay? Along the way, as mentioned, we can have the wires, we can have fuses, switches, transistors, relays, and the body of the vehicle or engine itself. The illustration here is showing what it would be like if the body of the vehicle or the engine were a part of a circuit. We can see the wire coming from the battery to the bulb, and then from the bulb and being attached to ground here at the body of the vehicle or the engine block. That's what these three lines, when you look at a wiring diagram, represent. That's where a wire is attaching to a ground point. We see that ground here continuing and the wire back to the battery, giving us that complete basic circuit. Now, people will often use the term, oh, there's a short circuit, meaning that there's a problem. Short circuit has its own specific definition that we can get into if I'm working with you as your trainer. Let's talk about open circuit, okay? An open circuit. Well, intentionally using a switch to create an open circuit gives us a way to turn that light bulb on and off without having to disconnect the wires or take the bulb out. A switch, picture it being closed, and when that switch is closed, it provides a complete path, and when it opens, then there is no path for the current from the source to flow through to the bulb, so that's an open circuit. So a switch essentially gives us a way to intentionally create an open circuit so that we can turn devices on and off. Now, what about when we have an open circuit that we weren't expecting to have, right? Well, any open circuit is going to prevent the flow of power from that source to the load. So obviously a broken wire, or if through the bulb itself, if the filament's broken, or if possibly the fuse has had too much power flow through it and is burnt, as everybody calls it. It's open circuit now. Here on the bottom, we see what looks like an intact wire attached to a stud, but if that stud and that terminal at the end of that wire, if there's too much corrosion there, it can insulate that circuit and not allow the power to flow through there. And again, creating an open circuit due to the extremely high resistance of that connection point. And then the last one down here in the bottom right corner, a loose connection. Sometimes it's making connections, sometimes it's not. That would be maybe if you've seen a semi-truck and trailer going down the road at night with the trailer lights flashing. Good chance that's some sort of loose connection, or maybe a corroded connection that's occasionally making contact. Again, just think of open as like there's air, physically open in the circuit. There's not that complete path from the source to the load and back to the source. All right, we're going to look at Ohm's law now. And this is where I have to be very careful and try not talk too fast, but at the same time not make this video drag out for 3 hours. So what you're seeing on your screen now is the textbook or electrical engineering way of learning Ohm's law. You can see we have this circle with E, I, and R, and those represent a part of Ohm's law. Ohm's law was invented by a German scientist, George Ohm. So after he discovered it, made it known, and it started being used, excuse me, it was named after him, Ohms, so it's O-H-M apostrophe S because it's named after George Ohm. And again, this is the textbook way of learning Ohm's law. So we see here that E, up here at the top of the circle, that represents electromotive force. And I is for intensity, and R is for resistance. And you use this circle like this, with this T drawn into it, to remember how to work Ohm's law. And I'll show you another way to draw Ohm's law in a minute here, but let's stick to the textbook way for a couple more minutes. So I, right? That intensity, that would be the amount of amperes or current flowing through a circuit. E would be the voltage, the electromotive force. And then ohms, the amount of resistance. There's many different ways to conceptualize Ohm's law and the way that voltage, amperage, and resistance relate to one another. They work in a 1-to-1-to-1 ratio. Okay, so to give you a very basic overview to start thinking about particularly volts and amps, picture you have a garden hose and it has 50 pounds of water pressure in it flowing through it, and you're watering the lawn. Okay, that 50 pounds would be like the voltage. Now picture you have a 2 or 3 inch hose like a firefighter would use to put out a fire. And it also has 50 pounds of water pressure in it. But you can probably visualize that you're going to have a lot more water flowing through there. That additional volume would be the rate, or in this case, in terms of electricity, the amperage. Okay? Now picture you have that hose and you start restricting down the flow of water through it. That's simply resistance, and we measure those in ohms. The 3 illustrations here at the bottom indicate how to use this circle to remember. Whenever you're going side to side, you multiply. Whenever you're going top to bottom, you're taking the top number and dividing it by one of the two below it. So if you know 2 of the data points, you can calculate the third using Ohm's law. Let's look at that a little bit closer here. VAR is my way of writing out Ohm's law to use it in the language we use every day in the shop. Volts, amps, and resistance. The same thing can apply here. So you can see in this bottom right here, the person with their finger over the R, they're trying to figure out the resistance of a circuit, which would mean they would already know the voltage and the amperage. So they're going to take the voltage, divide it by the number of ohms, take the voltage and divide it by the number of amps. See, I told you I have to be careful when presenting this material. And that's how they're going to calculate the resistance. Over here you can see they do not know the voltage, so they're going to divide the amperage, or multiply the amperage times the resistance. Okay? We multiply when we're going side to side, we divide when we're going top and bottom. So for the last one here, they have their finger over the amperage, so they're going to be dividing voltage by the resistance, the number of ohms. So let's look at that a little bit more written out here. You can see there's only one time that we're multiplying. When we're trying to determine what the voltage is, we would multiply the amps times the resistance. That's that side to side here in the Ohm's law illustration. But if we're trying to determine what the amperage is, right? So we have our finger over the A. We're going to divide the voltage by the resistance. Likewise, if we're trying to figure out what the resistance in a circuit is, so we have our finger over the R, we're going to take our voltage and divide it by the amperage. It's a 1:1:1 ratio, so there is no addition and there is no subtraction. You're either multiplying amps times resistance, or you're dividing voltage by amperage, or you're dividing voltage by resistance. Let's put it into play. So if the load of this light bulb circuit is 6 ohms and the battery has 12 volts, what is the amount of amperage that will flow through the circuit? So let me put that more into illustration here using the cursor. What we're saying here is that we've disconnected these two terminals from the battery. We went and got our ohm meter and measured the resistance of this circuit from here through the bulb, through the grounding point in the body, and back through and over to this point with it disconnected from the battery. If we're going to measure resistance with an ohm meter, it has to be an open circuit at that point, meaning there can't be current or voltage flowing through the circuit. It needs to be a circuit that's currently not flowing power so that we can then use the ohm meter to do that. The reason is the ohm meter, if you have a DVOM, a handheld volt ohm meter, it is going to apply power to that circuit and see how much returns back to the other side of the meter and to give you that resistance. So when these terminals were disconnected from the battery, 6 ohms was measured is what we're saying here for this sake of this introductory video. While we had the battery disconnected, we took our meter and we switched it over to voltage, and we measured from one terminal on one side with the black lead of the meter, and with the red lead we put it on the positive side, again with our meter set to measure voltage, and we measured 12 volts. So using Ohm's law, we know the voltage and we know the resistance of this circuit. So stick with me here because there's going to be a question at the end of this presentation, and I ask you to reach out to me with your answer. Send me a message through the website, through Facebook, or even call or text me and we can discuss your answer. So you understand where we're at now. We have 6 ohms in this circuit of resistance, which would be all the way through, and 12 volts of supply. Okay, I've rambled on long enough. Let's see what your answer is and if it compares to mine. I'm saying that we took the 12 volts right here and divided it by the, we took the 12 volts, yes, and we divided it by the resistance, okay? And we came up with 2 amps. We were trying to determine what the amperage was flowing through this circuit. And you're going to see here in a minute how you can use this actually in the workshop. This is not useless information that automotive instructors give to students just to give you, brain funk or anything like that, that this is used. And this is the most classic example that I could come up with in terms of not only how to explain Ohm's law and but also how to use Ohm's law in a potential real situation in the shop. Okay, notice the illustration has changed. We now still have our complete path. It's no longer going through the body, but we have the wire coming through, and there's a fuse, and then the bulb, and then there's our complete circuit back to the battery. Okay, so we came up with 2 amps is going to flow through this circuit. We had a good fuse, we had a good bulb, and we had 12 volts of source voltage at the battery. We calculated this circuit when we connected it is going to flow 2 amps. Now this is where I like to mention that if you have experience in working Ohm's law and working with incandescent bulbs, a traditional light bulb with a filament in it, you have to cut me a little slack right now. I am aware that a light bulb, an incandescent light bulb, the resistance changes after it starts heating. But for the sake of this discussion and this introductory video, we're just going with the fact, the assumed fact that the bulb has a constant resistance. Because the circuit measures, 6 ohms. So we know that at least starting out, it's going to flow 2 amps. All right, getting back on track now. Now, what if you had, the reason you were doing this test was because you had put a new fuse in and it immediately popped. Okay, it burnt. Too much power, too much current went through that fuse. And you go and you look and you see on this fuse over here that there's a 1 on the end of it. Okay, should you be looking up the specification for the fuse? I think so, right? We don't just go and jam a 2 amp or a 5 amp fuse in there because we might overload the wiring. So you go and look it up and you find that the 1 amp fuse is the correct rating fuse. Okay, here comes the question. What are you going to look into next to confirm this circuit is healthy? And what would be your first suspect in terms of what you would want to go to next? My name is Brian Wampler. I'm available to you at autoshopteacher.com or 918-689-8600. I thank you for watching and I hope to hear from you soon. Have a great day.